Today is the last course, and I'm going to go over all of the things we saw during the whole semester, especially the hard parts and the important parts. So you can see today, if you listen carefully today, you will have almost already studied for the exam, okay? So this is, I'm going to show you many examples, code examples of things that were important, but also subtle and maybe hard to understand. I'm going to start by talking about all the paradigms we saw, then the advanced algorithm design for declarative paradigms, data abstractions, multi-agent programming, and shared state concurrency. So let me start by presenting the paradigms we saw in this course. We saw declarative paradigms. They are sequential functional programming, sequential functional programming with data flow variables, deterministic data flow, and lazy deterministic data flow. These are all the declarative paradigms. They go from the classic one, this is the one you see in most languages, to the most expressive one, lazy deterministic. Then we saw non-declarative paradigms. The best one, which is deterministic data flow with ports. Then multi-agent programming. And shared state concurrency. So these are all the paradigms we saw in this course, and we saw many things that you can do with them. So what I want to show you now is some of the special properties of the declarative paradigms. It's clear that you should write most of your program like this, okay? Even if the languages do not help you to do that, that's what you should do. And in fact, you can do a lot. And after showing you the paradigms, I will show you the advanced declarative algorithms. And I will maybe show you some things that were hard to understand during the course. Okay? So the first thing I want to say is that sequential functional programming, the first paradigm, this is the one that you will see in many programming languages. Scheme and L are the most popular ones, but there are other ones like Clojure and so on. One we saw, especially in this course, is we added data flow variables. And I want to show you why this is very important. This is still declarative because you can only assign these variables to one value. Let me show you why this is important. One reason is that list functions are tail recursive. Okay, if you look at Append, the Append function, let me write it here, and then I'll show you why that it's tail recursive. X, S, and Y, S are lists. Excess of nil, then Y, S, otherwise, X bar, X, R, and we have X bar append X R Y S. Okay? This is the way you write it with a case statement, two cases, and in many programming languages like Scheme or ML you would write it in a similar way. But if you have data flow variables, this is actually tail recursive. This I explained already, but it's very, very important, so I explained it again. If you look at this recursive call here, you can actually write it in a special way. Assume now that the whole thing is a procedure. I'm going to write it now in kernel language, XS, YS, ZS. So the result will become visible in the head of the procedure. Then we can write it like this. ZS, which is the result, is equal to X bar ZR, and then we have a recursive call. Append XR, YS, ZR. So you can see that the creation of the result is done before the recursive call. This is possible because ZR is an unbound data flow variable. Okay? That makes it possible, and this is done automatically. So all these functions will be tail recursive. Why is that so important? Tail recursive means that it's basically equivalent to a while loop. That means the stack size is constant. So that means that it's an efficient loop. That's already interesting. If you want to do a function like append efficiently in a classic functional language that does not have data flow variables, then it's harder to write. It's more difficult because this definition would not be tail recursive. So it's equivalent to a while loop and stack size is constant. Why? That's already interesting, but why is that even more important than it seems? Because it allows deterministic data flow. It allows agents, declarative agents, concurrent agents. The lists become streams. List becomes streams, which means they don't end. They are constructed incrementally. They are communication channels. So an agent will have an input stream and an output stream. And this agent is a list function executing in its own thread, like append, using data flow variables. And this will have a constant stack size, which means that you can write concurrent declarative programs. So the data flow variables is what makes deterministic data flow possible. Okay? That's one thing I want to show. Many languages nowadays, you see these more and more. Okay, this is something that programming languages don't always understand, but nowadays you see these more and more. This is sometimes called futures or promises. Okay, these unbound variables, and this was actually invented a long time ago, but somehow, for historical reasons, it got forgotten. But nowadays, more and more in large distributed cloud databases and so on, you see this coming back. So you're going to see this. Even if you don't see it today, you'll see it coming back. Okay, that's one thing I want to show. That's the first thing. Let me show you a second thing now. Again, because of data flow variables. The second thing is constant time append function. If I normally do an append of two lists, and if this list has a length of n, this will take some constant times n time, because you have to traverse the whole list, and because it's declarative. That's not nice, and that kind of breaks the whole interest of using declarative paradigms. If you can't even do something so simple efficiently, then why use declarative paradigms? Okay. But this is actually solved if you have data flow variables. With data flow variables, you can represent the list. You represent the list as two variables, which is called the list difference list. So the list, for example, A, B, C would be represented as two variables, S and E, where S is equal to A, B, C, and putting E at the end, and E. Okay, so you represent it as a partial list where the end is an unknown variable. And now if I want to do an append, if I have, for example, Sx and Ex, this is one list, and I have Sy and Ey, the second one, I can append them very easily. All I have to do is bind the end of the first one to the beginning of the second one. So Ex equal Sy will append. Okay, we'll append them in constant time. Of course, you can only do this once. There's only one version. We say that this is an ephemeral operation. You can only do it once. But that's okay. In almost all cases, it's okay. And even in a stateful language, if you want to do this constant time, you can only do it on one version. If you want a second version, you will have to actually create a copy of the first list in any paradigm. So this is a constant time ephemeral append operation. And this is made possible because of data flow variables. Even if you don't have concurrency, if you have sequential functional programming plus data flow, even in sequential language, this allows you to make a very efficient declarative programs. Okay? That justifies the data flow variables. It shows why they are important. And the point is, of course, that difference lists are still declarative. They still have all the good properties of the declarative paradigms, which I will explain in a few minutes. They have all those good properties, don't go away, because you have only one, you can only assign to one value. Okay. Let me now, we have now deterministic data flow, so you add threads. Here, with this paradigm, you can actually create concurrent programs, agent programs, with streams as input, pipelines, and other kinds of programs that we wrote. We've actually had examples like digital logic simulation, which is using exactly this paradigm. Digital logic, the way it runs, it's all clocked. That means all ports are getting a value at the same instant in the clock, and then they compute the next instant, and so on. So all processors are written in this way, which basically is using this paradigm. Of course, it's deterministic. It's a completely deterministic paradigm. But very much concurrency can be done like this. Okay? So that's the deterministic data flow, which is very important. And again, it's a paradigm that is used more and more. And now, 20 years ago, it was not used so much, but today it's used a lot. And if you do cloud analytics tool, you will almost always be using this one. Okay? Let me now say a few words about the lazy version. Okay? So the lazy version of this adds demand-driven it adds an operation which is adding to the data flow. For example, let me explain how the data flow works in the usual deterministic data flow, semantics, if I do C equal A plus B, an addition operation, okay, in deterministic data flow, the way it actually compiles is I will do a weight A, a weight B, I will do then a primitive add operation, which will do A plus B and put it some other place like X, and then we'll bind, an operation bind C to X, okay? This, you can see this as the semantics of the data flow. The wait operation will suspend the thread until A is a value, till this variable is bound, and B also. And once A and B are bound to numbers, I can do a primitive add. So this is the instruction in the machine. And once I've done the add, I do a bind operation, and this one basically tells all the wait C's to continue. So the bind operation will basically tell the wait that they can continue. So semantically, the data flow is all implemented like this. Of course, the compiler can very often remove these so they don't give overhead, huh? But this is the semantics. Now the lazy adds one operation to this, which is called wait needed. Wait needed X. You basically suspend the current thread until another thread does wait X. You see, this is quite different from wait. You see, the wait will suspend until A is bound to a value. But wait needed X will not do that. It will suspend until another thread is doing wait X. So we say that X is needed by the other thread. Okay? See how that works? I explained it already, but this I know from experience that people, they don't always understand really the difference between wait and wait needed. So wait needed is a special kind of operation, and it's actually very easy to implement because these unbound variables, each unbound variable will have a queue of suspended threads attached to it. Okay? So the wait needed X will just have to wait until there is at least one thread inside that queue. If I do wait X, then the thread will be added to the queue of X, and wait needed will suspend until there's at least one thread in that queue. And laziness is implemented by adding wait needed to wait and bind. This you can see it as the semantics of laziness. Okay, so that's one thing I want to explain. Now let me explain another thing for what you can do with laziness. There's many things, of course, you can do with laziness. Let me just explain one thing here, which is the bounded buffer. Okay, assume I have a producer and a consumer, and there's a stream communicated between the producer and the consumer. Okay, and the consumer needs the values from P. So this is actually, if you do it like this, there's sometimes a resource problem here, because P will just keep producing forever, and if C is very slow, then all the elements computed by P will stick around and overflow the memory. Okay, that's one thing. But sometimes P is very slow, and when P is very slow, C has to wait. So you see there's some kind of a flow problem here that can give memory problems or speed problems. Okay. It can maybe sometimes cause overflow memory, or it can cause speed problems. It can cause system to slow down. Maybe P produces some elements very fast, but then it's very slow after that. Okay? So this is actually a problem. And the bounded buffer was invented as a kind of intermediate node to solve these problems. So you put the bounded buffer in the middle of this, okay? And then you change this to make it lazy, to make it demand-driven. You can make the first one lazy also, if you want. If you make the first one lazy, then you will have no memory problems. Remember, there's two possibilities. If you make this eager, then nobody is stopping P and sometimes overflow memory. But if you make it lazy, there will be no memory problems, but then you have speed problems. Because P will do nothing unless C asks for something. So if C is not asking, if C is computing, then P will do nothing while C is working. So you have a co-routing. In fact, you have a single control moving back and forth, and P and C will never execute at the same time, okay? C asks for an element from P, P computes it, but while P is computing, C is waiting, okay? So the lazy solution will have no memory problem, but it will cause co-routing, so you have a speed problem. You will slow down the system. Whereas the eager solution has no speed problem. Nobody is stopping P or C from running, but nobody is stopping the memory from overflowing, okay? And if you want to have both, if you want to have both low memory utilization and high speed, then you need a bounded buffer. So the bounded buffer has a size, has a fixed size, and the bounded buffer basically always tries to fill itself up. So compared to the producer, the bounded buffer looks like a consumer, and it will ask for elements, okay, until it's full. So there's a certain number of elements, so you have a fixed memory size. And the consumer, if it needs an element, it will immediately get it from the bounded buffer. So you can see that the bounded buffer will keep some elements around, and if the consumer asks for elements, they will get it immediately. And if the buffer is full and the consumer asks for one element, then the bounded buffer will ask for another element from P because it's not full anymore. Okay? So you can see this, in most cases, will solve this problem here. It solves the speed problem because P can get ahead of C. P can produce more elements than C. And it solves the memory problem because there's a limit to how far P can get ahead. Okay? So you can see it's a combination of eager and lazy, actually. And in many cases, it solves the problem because usually there's fluctuations in speed between P and C. So the bounded buffer will not always be completely full, for example, and not always be completely empty. It's always kind of fluctuating. This is a concurrent declarative program. You cannot write this kind of a program in a pure, lazy language that's not concurrent, because the producer is independent of the consumer. Concurrent means that there's independence. That means the producer can get ahead of the consumer. There is a slack, if you want, between producer and consumer. The producer can keep running even if the consumer asks for nothing. Okay? So this is concurrent, and it's also declarative. It's completely deterministic and functional, basically, because it's using just the weight needed and the data flow variables in the basic semantics. Okay? So in lazy deterministic data flow, you can implement declarative bounded buffers, which are actually very interesting, already kind of sophisticated concurrent patterns. Okay? Very good. Okay, so that's what I want to say. First thing about declarative. Now let me say something about algorithms, advanced declarative algorithms. Sometimes people criticize declarative programming because they say you cannot write efficient algorithms in it because of the single assignment. That's actually not true, okay? And let me show you now some examples of that. Advanced declarative algorithms. what I want to show you now, so is things we saw already in the course, but maybe we're a little bit complicated. So the first thing I want to explain is the difference between an ephemeral versus persistent data structure. Actually, ephemeral versus persistent algorithm. Let me say it like this. Ephemeral means you can only have one version at any time. That means if I have a queue and I do an insert operation from Q1 getting me Q2, as soon as the assert returns Q2, then Q1 is not valid anymore. I cannot use it anymore, okay? There's only one version. So Q2 invalidates Q1. I can only have one version. And most algorithms that you use will be ephemeral. Many times you only need one version, okay? But sometimes you need more than one version. In a persistent algorithm, you can have multiple versions of the data structure. For example, if I do Q1 and I do insert, and I get Q2, then Q1 is still okay. I can also do another insert, and here I do A, B, this gives me Q3. Now I have two versions, okay, and I can do this, and I can even have more versions. Sometimes you can even have a merge operation, which combines two versions back into one version. That's also possible. You can have multiple versions. This is sometimes useful, and there's actually many cases when you want this. For example, collaborative work, applications. Two people are editing the same text. Maybe they're offline, so you have two versions of the text. And the two versions are going to exist at the same time, and then when they go online, then you have to merge the versions, okay? Or you have things like GitHub. When you do software repositories, you can create branches, you can create multiple versions, and you can also merge them back, okay? So this is typically the kinds of things you can do. See if there's any other. Also in databases, yeah, you have sometimes need for multiple versions. If I have a collection of data that represents a software item, an airplane, for example, okay, very complicated. Now I want to make a new airplane which is modifying that, but some other team wants to make another kind of airplane that also modifies that. I could make a copy, but if the airplane data structure is huge, then maybe I don't want to do that. And many databases actually support kind of versioning operations, okay? So the versions are sometimes useful, and so it's sometimes interesting to have algorithms that have multiple versions, okay? Now, let me show you now some of the things we did there, okay? We have, let me explain also the difference between amortized versus worst case time complexity. This is an important axis too for algorithms, okay? So an amortized algorithm will, on average, have a complexity. So what does that really mean? So let me explain. So let's say you have an amortized, let's say I have an algorithm, okay? I have n operations of the algorithm, okay? And these n operations are sometimes constant and sometimes taking one. So for example, if I have operations that are constant time, O1 operations, and then I have operations that take n time, then these operations are expensive, okay? For some number n. But in some cases it's okay. If I have n operations, and the number of ON operations is a constant, then the total time will still be order n. Okay. So that means because the total time is n, you can actually, on average, for an operation, it would be constant time then. So let me make a more formal definition of this. Okay, if n operations, let's see, what's the simplest way to explain this? Okay, if a sequence of n operations has a time, total time of Fn, some function of n, then we say that one operation has an amortized time of OFn divided by n. Okay, so we basically spread out the Fn over the n operations. If you have a Q data structure and the operations usually are constant, but sometimes there's an order n operation, but there's not so many of them, then it could still be amortized constant time. Okay? So that's the definition of amortized. Worst case, of course, is something you know. Worst case time complexity is when every operation takes a certain time. Okay? Now let me show you what the different declarative paradigms can do. Okay? We have an example of a Q data structure, Q abstraction, with insert and delete operations. And we showed how to implement that in certain kinds of constant time. Okay? So there's actually some kinds of constant time. Let me show you a diagram, and then I'll explain why it's like this. If I have a standard sequential functional programming paradigm, which is the first one here, then I can make an amortized ephemeral algorithm, constant time. Okay? It's not worst case constant time, because sometimes you have to do operations that are order n. And now, if you add data flow variables, let's do sequential but data flow, then you can make it worst case constant ephemeral. So the going from sequential to sequential plus data flow turns the amortized into worst case. Okay. On the other side, you can add lazy execution. And what lazy execution lets you do is turn the ephemeral into persistent. So you can have an amortized persistent version. And if you're clever, in many cases you can also make worst case persistent. Okay? Okay? So basically, going from sequential to sequential, so this is lazy. Sequential functional programming. The laziness gives you persistence, and the data flow variables gives you worst case ephemeral. So the data flow lets you go from amortized to worst case, and the laziness lets you go from ephemeral to persistent. Okay, so that's a summary of what we saw, but let me explain how it works now, because I think that people, maybe it's hard, it's a little bit subtle to understand how it works. So let me explain that. Okay, so let me start by the standard one, the amortized ephemeral. The way it works is that the queue is represented by a tuple with two lists, the front of the queue and the back, the reverse of the queue. And when you insert, you add an element here. And when you delete, you remove it from the front. Okay? So the insert is constant time. When R is always non-empty, you can always do insert in constant time. The delete is constant time if F is non-empty. Okay? So if I start by nil, nil, and I do an insert, then I get, for example, nil, A bar nil. But if I want to do a delete now, then this one is nil, so it doesn't work. So I have an operation that lets me move from the reverse list to the front list. Okay? So occasionally, what I do is I can actually move from R to F. So if F is nil, so Q nil R is transformed to Q reverse R nil. Okay? The elements I add in the reverse, I have to put them at the end, because the ones that are in front here are actually back of the queue. Right? So I do this, and this is done inside the delete operation. Okay? If this is nil, I do like that. Now, of course, this takes time, and if the R has a length of n, this takes a time which is proportional to n. Okay? And that means that the delete operation sometimes is expensive. It can take order n. If I do n inserts and one delete, then the delete will be doing order n. Okay? So basically, if you look at it like this, if I do, let me make a diagram. If I do a sequence of inserts, and then I do a delete, all these are going to be constant time, but there might be n operations. And here I have a delete, which is going to be n, order n time, proportional to n. So you can see the total time is still order n, and it's amortized constant time. Okay, right? You get it, huh? So that's the easy case. Now, let me show you the other cases. Okay? The worst case ephemeral also is easy. The hardest one is the lazy. This one is also easy because we basically use a difference list. So because we're using the data flow variables. So the queue is represented as a front and a back. But the front is equal to some elements that are in the queue. And then there's the back, and then you also have the number of elements, because otherwise it's not possible to know whether the queue is empty or not in a declarative way. So these two are a difference list, and the insert and the delete are both constant time. To insert, you basically have to add to the R. So that basically you have to bind R, so the F stays the same. So let's say I insert C, so the F becomes A, B, C, R prime, and here I have R prime, and now the length is 3. So for the insert, basically I'm changing the R to R prime, and I'm binding R, okay? And for the delete, I remove this one. So now I have B, R, R, and now I have only one element. So you see, for the insert, I'm updating the second variable, and for the delete, I'm updating the first one. And notice that this is ephemeral. You cannot use it more than once, okay? Because if you use it more than once, they will interfere with each other, okay? So that's very fine, right? So that's efficient, huh? This is actually, most of the time, this is good, huh? So if you're only doing ephemeral, difference list is basically solving the problem. It makes it very efficient. You see the data flow variables are solving this efficiency issue. But let me now talk about persistent, okay? Now, let me now go to amortized, persistent constant time. Let me first show why the first one, this one is not amortized persistent. Okay, let me show this first. And this was actually a question on the midterm, if you remember. Okay, show me why it's not amortized persistent. Well, you have to come up with a sequence of operations where you have multiple versions, and you can show it's not amortized. So let's do a sequence of inserts again. Okay, I have a sequence of inserts now, n inserts. These are all constant time, huh? But so far I have only one version. Persistent means I can have multiple versions. Well, let's make some versions now. Let's say I do a delete here. I do one delete, I do another delete, I do a bunch of deletes. Okay, I do order n deletes here. Now each of these deletes will have to do a reverse. Each of these deletes will be O(n) time, constant proportional to n. So this is actually n squared time. So if you look at the whole thing, I have n plus n, 2n operations, and the time is n squared. Well, if I divide it, then the average time is n over 2. It's not constant, right? So you get it, Okay, so it's not, so the solution we had before is not amortized, persistent. So how do we solve that? We can actually solve it by laziness, okay? By using laziness, amortized, persistent. And what's the property of laziness that we use? Well, we can create a computation, but we only do the computation later when we need it, okay? So basically, we create the computation that does the reverse, okay? But we don't actually do it until we really need to do it, okay? So the delete operation, when you do this, sometimes you don't need to do this reverse, okay? But you only spend the time when you actually need it, okay? Okay, so if you remember, let me refresh your mind on how the amortized persistent queue is implemented. Okay. So in this one, you have a tuple again. You have the length of f, length of r. Okay. Here now we have a tuple of 4 elements. We have f and r, but also these lengths. Why do we have it like that? Because sometimes these are not actual lists. Okay, these can be lazy computations that when you execute them make a list. So there may be lazy suspensions, these F and R. There could be. And so that's why you want to know the length. Also, you don't want to compute the length. Even if they're lists, you don't want to actually compute the length. Huh? So you keep track of the length, basically. So when you're doing it in a sequence of inserts, the way it works is that occasionally, so again, the inserts will add to the R, and occasionally you will make a computation. So you will, in some places, put in a computation moving R to F. You put it in there occasionally, so you're putting it in at some point in time. If you notice the way it works in the code, that you keep track of L length and F and R, and so when each time you do an insert, you have, for example, len F is some value, and then R is basically 0. Each time you do an insert, this increases, and when the length of R gets big enough, then you move. And the reason why you do that, when they basically are almost equal, that means you've actually paid for the reverse, okay? If you do this, then you will only do reverse when you actually have already these elements. So you've actually already paid, you actually already have n things here, so you're allowed to do n more things, okay? So this is what's called Banker's solution to an amortized algorithm, which means if you want to buy a house, okay, you put money in the bank, and when you have enough money in the bank, you buy the house. So here, if I want to do a reverse, that's expensive. Each time I have an element here, I have money in the bank, and when I have n elements, I'm allowed to do an n reverse, okay? So that's one thing. So I'm not going to say more, but if you should look at it more in detail. Okay. But now I have multiple versions. Okay. Now I have multiple versions here. So what's going to happen? So let's say I have an I here. I have multiple versions. Again, I have a bunch of D's here. Okay. And the D's are each deleting, but you have many versions now. Okay. So, but the D's they will only create, so these lazy computations exist, but the D's will only do a part of the computation that they need the element, okay? So first of all, so this is lazy. So the move here is basically, it's doing an append and a reverse, huh? If I have F, R, it goes append, reverse, R to F, something like that, huh? It's doing something like this. I think that's the right formula. It's appending it. No, sorry, the front. It's at the back. This is not right. So you're doing append F, and the reverse of R comes at the end. Okay? So this is the operation you're doing. This append is lazy, and the reverse is not is lazy, but it's monolithic. Remember, it's monolithic. That means if you need it, you have to do the whole thing. So this is a lazy, but this whole thing is a lazy computation here. And when I need an element D, I do one part of this. I'm only doing a small part of this, okay? And then I actually bind the result to the F, and so all the other D's will see the same thing. You see, if one delete does something, all the others will see the same thing. And now if I keep doing inserts after, so you can see the lazy append will execute, and the value is bound to a variable that's in common, so everyone will see it. But assume now you have a bunch of i's here, and eventually you exhaust this and you do reverse. Okay? But you will have enough i's to pay for the reverse. Okay? You will, the length of f and r are going to be the same. So when f is empty, then you will have to do reverse after. Sorry, I'm doing deletes here. Sorry, I'm doing deletes. These are deletes. I'm removing elements, and I start by removing elements from f. And when f is empty, then I do the reverse r. It's a lazy computation. I only do when I need it. So when I do the reverse, I've already gone through n elements here, which means I paid for the reverse. Okay? So this is paying. So the reverse is paid for. Okay? It's paid for because you have done n, you have removed the n. Because of the way these computations are done, the f and the r are the same size. Okay? So this works. And so the reason why it works is that the computation is done only when you need it after when it's created. So it's created here. So this computation is actually shared among all the versions. So it's not like in the previous case where each delete had to do a reverse. Okay? Here, when the delete does a reverse, it's shared because it's created during the inserts. Okay? So because this is a shared data flow variable, when the first delete does its thing, the others will see the result too. So the result is shared among all the versions. Okay? And you will only do the reverse when you have done enough deletes, so it's paid for. So the reason why the laziness makes it persistent is because it lets you share the results among all the versions. Okay? So laziness lets you make things persistent. Okay? And then there's a final thing where you can actually be a little more clever. The reverse is monolithic. You can actually make it worst case persistent in this case. This depends now. This is not always possible. This is possible because you can take the append and the reversed and turn it into a app-rev, which is not monolithic. So the reverse is monolithic, which means that even if you make it lazy, you have to do the whole thing. You can't do it piece by piece. Whereas the append is incremental. That means if you only need a small part of the result, you're only going to do a small part of computation. And if you do, you can actually combine these two so that each step of the append does a small piece of reverse. So the app-rev will become incremental. Okay? And this actually spreads out the cost of the reverse over all of the deletes, in fact. Instead of doing it once, you've spread it out, and so it becomes worst case persistent. Okay? So incremental lazy, I kind of see it as putting butter on a piece of bread. If I have bread and I put a lump of butter on one side, that's the computation. With the laziness, I can spread the butter so it's very smooth over the whole thing. Okay? Is that clear? Maybe it wasn't so clear during the lecture. So is that better now? Do you understand better why the laziness? You can always look at the video, of course. Why laziness lets you do persistence? Okay? Because of two things. One is that when you create the computation, you don't do it yet. You only do it later when you actually need it. And when you do that, then maybe you've already paid for it. But also, if you create multiple versions, you create a computation, you create multiple versions, then the result is shared among all those versions. So you only have to do it once. Okay? So the laziness lets you do that. Okay, so that's why the laziness lets you do persistence. Okay, so summarizing, you can see that using these techniques of lazy and data flow, you can build very efficient declarative algorithms. So there's basically no reason to do non-declarative, except that your language maybe doesn't support declarative, huh? But otherwise, there's no reason. You can do it all declaratively and keep the advantages of the declarative paradigm. Okay? Okay, let me make a break now. And after the break, we'll move to more non-declarative things. Okay? The course, now we go to the beyond declarative, okay? I'll talk about non-declarative, but first I want to explain a few things. First, why do we do declarative? Why is declarative important? There are many reasons why declarative is an advantage, is important. It's why functional programming, in general, why is declarative advantageous? Simple things like testing. Testing is much easier on a declarative program because a declarative program is basically, your program is like functions. You can test, all the parts can be tested separately, okay, for correctness. Because each part is a function, and this is not true if you have stateful parts with memory, okay? So not true if the parts have memory, which are non-declarative, huh? If they have memory, then they interact. If one part, like an object in Java, it has an internal set of attributes, and they can get weird values. So if the parts have memory, then the whole history, so the whole sequence of operations is important. Okay? Because past operations can change the internal state of an object. Whereas in a declarative function, the function does not change. So it doesn't matter what you do in the past, the only thing that's important is the argument. Okay? So testing is much easier in a declarative programming and really, really much more efficient. Okay? Another advantage is it's deterministic. This is something we saw before, which is called the Church-Rosser theorem. Okay, I'm not going to say exactly what it is, but basically all declarative programs are essentially doing computations in a very simple language called lambda calculus. So declarative programming is basically programming in lambda calculus. All of these, this is just syntactic sugar for lambda calculus. And in lambda calculus, the result is always the same, independent of which order. That's why all these concurrent paradigms are still deterministic, even though you have multiple threads. And that's really very important, okay? This is something that I call concurrency for dummies, okay? That's not an insult, that's a compliment, huh? That means as long as you can, you should use declarative programming, even in concurrent system, because of this very important result. So declarative programming is really a paradigm. It's not just an arbitrary thing. It's based on a very strong, formal, mathematical foundation, okay, all this. It's based on a strong mathematical foundation, the lambda calculus, and you prove properties, and the very strong property that you have is Church-Rosser. So it's not randomly because of because we like, because we're masochists that we like to do declarative programming or something, huh? It's because it has this really strong property. It's fundamentally a strong paradigm, okay? With this very strong property. That's why it's important. But the strength is also the weakness, as usual, huh? Very often it's like this. Even Superman cannot stand the kryptonite, okay? So there's also a kind of kryptonite for declarative programming. So the limit of declarative programming, so one example that I showed you that you cannot write in declarative is the client server. It's one out of many examples, and I want to show it again because it's kind of subtle thing, and I want you to really understand. So I have a bunch of clients, 1 million clients, let's say, okay, all talking to a server. Maybe it's over the internet. You're ordering things on Amazon or something. So each client sends a query and gets a response. Okay? Query and response. So this is a very common kind of application. And the clients are independent. That's very important. The clients don't know each other. They're independent. Okay? So there's a requirement for this. The whole problem comes from this requirement that the performance of a client, so the round trip time for a client only depends on the network properties and the computation that the client does at the server. That's very reasonable, huh? Each client does a round trip, and it only depends on the speed of the network and on the computation done in the server. And there's no interaction between, they're independent. This is a very reasonable requirement. Huh? You want this. I don't want to be blocked because somebody else is doing something. I want to have this property. Okay. Of course, it's a little bit, it's not completely perfect because if the server is handling many clients, it will do more computation, so maybe slows down a little bit. Okay. But the server can be parallelized so that you don't really notice that if you have many clients. So this is a very reasonable requirement. Now this program, the way with this requirement, you cannot implement it in a declarative language. It's not a question of performance, it's not a question of being clever in the programming, whatever. It's fundamental, okay? It cannot be done declaratively because of the definition of declarative programming. There is a contradiction. You cannot do it. Okay? So do you see that? Do you understand why it's like that? Somebody, do you understand? Who understands why it's like that? Some people, you don't. Oh, well, I'm very happy then to go over it again. Why is it not declarative? Well, let's say I have 2 clients, okay? Let's just say I have 2, and they're both doing query, and the queries are traveling to the server. The server does not know which client query will arrive first, okay? So this application has inherent non-determinism. And why is it inherent? Because it's coming from the clients. Coming from clients and the requirement, okay? I cannot remove this non-determinism because each client wants reasonable time. That means when this query arrives, I have to handle it. I cannot wait for the other one. Huh? When the query 1 arrives, I have to handle it. And when query 2 arrives, I have to handle it. Because of the requirement, okay? But I don't know which one will arrive first. It's non-deterministic, so non-determinism, you remember, is a choice that's outside of the control of the programmer. So I'm the person writing this application. I don't know which of these two will arrive first. It's not my decision, okay? The choice is coming from outside. Non-determinism is when there's a choice that's imposed. I don't have full control. Someone else has control. Here it's who has control? Well, I mean, it's the clients, but it's also the network. It's the real world has control here over my application. So no matter which query arrives first, I have to handle it. That means if query 1 arrives, I must handle it immediately. If query 2 arrives, I must handle it immediately. Right away. But I cannot write such a program in the declarative paradigm. How can I write the program? So let's say you have a server here, which has, let's say I can have multiple streams for each client. But let's say I have 2 clients, 2 streams. Case, now I have S1. Maybe I combine them in a pair, for example. Well, maybe I can assume that the query 1 arrives before query 2. Okay? And I handle it. But now assume that query 2 arrives before query 1. And then I handle it. Okay? Here I'm handling query 1, here I'm handling query 2. This will not work because the case statement is deterministic. All instructions in declarative programs are deterministic. They never make a choice. They do one thing. Okay? The case will test the first pattern, and if it's acceptable, it will do it, and only if the first pattern can never be done will it try the second pattern. The case is not trying all patterns at the same time, because that would be non-deterministic. The case is deterministic. Why is it like that? Because it's declarative, okay? It has to be like that. Otherwise it's not declarative. That means I will never try the second pattern here. Never. Because the first stream, until the first stream closes, until this S1 becomes nil, until the first client goes home and turns off his machine, that's the only time I will handle the second one, okay? Because otherwise I will never try. You see that? It's fundamental. It's not, of course you can implement a case that has more than one, but that would not be declarative, you see? I mean, a case that handles more than one, actually, it exists in an operating system. And in fact, if you want to listen on data coming on more than one socket, in Unix you have this thing called select statement, which maybe you've seen. Select lets you wait on multiple connections. So it's like a parallel, non-deterministic version of a case. But that's not declarative, okay? Of course you can do it, but it's not declarative. You lose all the advantages of declarative programming if you do that. So you cannot do that. You force yourself to do that, to not do that, because it's not declarative, okay? So this cannot be written. You see that? You see why it's like that? Is there...
And it's also from the operating system. So if Erlang not using select or...
yeah, so select is an operating system. But all operating systems have non-deterministic operations, of course. And I'll explain in a minute. The real world always can force you to be non-deterministic. So you have to handle it.
The beam engine from Erlang works way better than select.
Of course. Yeah, select is not very efficient. Yeah, so select is an operation. So that was the point. Select is an operation existing in Unix. But if you want efficient non-determinism, you should not use Unix. You should use Erlang. In Erlang, all the processes are non-deterministic and they're extremely fine-grained. So Erlang, of course, is much more efficient. I mentioned select because people know Unix and they maybe know POSIX and so on. But of course, if you want efficiency, you don't use that. You use Erlang. But which we saw in the course. Okay, so you cannot do it. Okay. And the point is the real world. Okay. It's because of the real world forcing you to be non-deterministic, and declarative is deterministic. Okay. So sometimes you have to be non-deterministic. And that's the main advantage of declarative programming. It's deterministic, okay? But the real world will sometimes force non-determinism. Can be non-deterministic, okay? Okay? Okay, so that's one thing that we saw. And how do you solve that? You have to make the paradigm non-declarative. So it is no longer doing lambda calculus, it is no longer obeying Church-Rosser, it's no longer deterministic, it's not anymore like that. So you give up the advantages of declarative programming. So the non-declarative paradigms, they add non-declarative operations. So the non-declarative paradigms, there's basically two ways that are popular. Okay, in fact, there's many ways to make non-declarative, but there's two main extensions of declarative programming. Of declarative programming paradigms that are used in practice. Why these two? Because they work well, because programmers, you can use them as programmers. I mean, there's many reasons. You can, of course, do many, there's dozens of ways to make non-declarative. One of them is called mutable state, and the other one is called communication channel. So the mutable state, everybody knows, it's variables that you can assign more than once, and we call them cells. And the communication channel is where you can send and receive on it. We call them ports. The main difference is that when you do an assignment, you forget the previous values, okay? Forget the previous values. Whereas in a communication channel, all values are remaining there. So the main difference between the two is that in the mutable state, when you assign a variable, you forget the previous value. It goes away, okay? But in a communication channel, when I do a send, the previous value does not go away. It's still on the channel. I extend the channel, okay? But that's like a philosophical difference. But both of these are non-deterministic, okay? So which ones do you use? Well, we saw in the course two main ways. One is multi-agent programming, which is based on ports. The other one is shared state concurrency, which is based on cells. And both of these are used in practice. Both of these are used a lot. So this one is maybe used a little bit more. This one can be used, for example, in Java. This can be used in Erlang. But there's many. This is actually used much more than just in Erlang. In parallel scientific computation, you have something called MPI, Message Passing Interface, which is also doing this. So both are actually used a lot. Okay. So these two solutions are both industry kind of standard uses. Okay. We saw also a formal a formal argument showing the need for extensions, for extending declarative programming. Because this is actually a fundamental thing, and we show a formal argument. Any declarative computation is a lambda reduction. Okay? So in theory, we saw the lambda calculus in a previous course, but all declarative programming is basically a form of lambda calculus, and you start from an expression and you reduce it until you achieve a result. Okay? You can see this as kind of a function application. This whole thing is basically doing some kind of a function application. You have an initial expression, a big lambda expression, if you remember. The encoding can be very big. And then you reduce according to very simple rules of lambda rule or evaluation, and until you achieve some kind of a normal form final result. Okay? So this is the lambda reduction. Now, you can immediately see, if you look at this in the right way, that there is some issue here. This cannot interact with the real world. This formal operation. Okay? This is actually implemented on a machine. This is this is a running program. This formal operation of lambda is a running program, running on a computer. And each of these reduction steps takes some time. So this whole thing takes time, okay? During this time, I'm doing only these reductions. So I cannot interact with the external world here, because that's not part of the lambda definition. I have an initial expression going to a final one, okay? That's it. So that's why this lambda reduction actually is it's impossible to interact with the real world. It cannot. And it's because of how it's defined. It's extremely straightforward and simple. Okay? Okay, there's ways to get around this. The people, of course, try to find tricks to get around this. You can divide your programming into small lambdas, etc. You can have streams. Streams is where things are coming in a certain way, as if they were part of the initial expression, and they're coming out in a certain way. So there's ways to get around it, but it stays. The fundamental issue stays. You cannot do any kind of general interaction. You can only interact if you can pretend that it was already there in Iwana. See that? If you want to interact, if you want to bring something in here, A, the only way to do that is to pretend that the A was already in the E. Otherwise, you cannot make a formal. It will not fit here, So, but very often you don't know the A here and in the initial time. If this is a client talking to a server, then and the server started yesterday. Well, nobody knows what the client is going to say today, okay? So this requires traveling backward in time, doesn't work, okay? So this trick doesn't work in most cases. You cannot just interact, things cannot just go in and out, okay? So we saw this in the course, and I defined different kinds of interaction. So you can actually extend this, but then it's not declarative. It's non-declarative in different ways. You can extend by certain interactions which are like mutable state, which is reading and writing in a register. You can extend with interaction which is like sending and receiving on a communication channel. Also, reading a hardware clock is also an interaction that's non-deterministic. If I read the time on a clock, the nanoseconds, atomic clock or something, then the exact time depends on the exact moment when I'm reading that. And so that moment, nobody can predict it. Okay? Question?
One needs to introduce monoid. It's for like Haskell does. Monoid.
Yeah, okay. So there's different ways of doing this. So yeah, so the question is, different programming languages, they have different ways of extending this. So the Haskell language, which is a functional language, has a very clean definition of declarative and interaction with non-declarative things. And it's encapsulated in a structure called a monad, okay? So in Haskell, this is made very clean, okay, this interaction. But I'm not going to talk about Haskell, okay? But in a language like Java, you just add these interactions everywhere, and you don't care that it contaminates your whole program. Whereas in Haskell, you make a very clear separation of the part that is pure and the part that is interacting with the real world. Okay? But that's a philosophical choice. In Java, you are supposed to be in the real world, and you're always updating things, so everything is potentially mutable. Okay? Whereas in Haskell, you're supposed to be completely declarative, and the real world is just an annoyance. It's something that you have to handle, but you don't like it. It's kind of on the side. Whereas in Java, you accept the real world, and your whole program is actually part of the real world. Okay, so it's a philosophical difference. Okay, so different languages solve it in different ways. Okay, so that's something we saw. So that's important. It's important to understand the boundary between declarative and non-declarative, because it's a real fundamental thing in programming. And many programming languages, they make different decisions with this boundary. Okay? So we saw three paradigms now. The best one is this one. Basically, most of your program will be deterministic data flow, or lazy deterministic data flow, and sometimes you need ports. You try to minimize the ports, because the ports is non-declarative. So most of your program is declarative. So on the client server, you can do that. So here's the client server again. Okay. In this whole client server, you actually only need one port here. Okay. So each client will do a send of the message to the port. And the port has a stream, and the messages will appear on the stream. And so the server will only have to read this stream, and all the messages will appear. And the port, the actual, is making a choice here. Which of these two will appear first? So there will be some order here. Which one arrives first? How do you know? Well, it depends on the speed of the network and which client is clicking on their web browser and so on. But one of them is going to be first. And so the port will expose this non-determinism. So this exposes the non-determinism of the real world here. One of these two will be before the other. Maybe sometime later it will be M2, M1 if you execute another day. One of them is going to be before the other. So there's a choice between these two. And this choice is now visible in the language. So we say the port exposes the non-determinism of the client choices. Okay? So it becomes visible in the language. So the port is non-declarative, because it exposes non-determinism. But all the rest can be declarative. The client can be pure program, pure declarative, this one too. The server also could be pure. Maybe not completely, because maybe there's a database with transactions here behind it. And again, this will need some extensions. So in a real world client server, the server is not going to be completely pure. There's going to be a piece of the database that's not pure because it's going to use a stable storage with transactions. And failures, failures like computers crashing, are of course non-deterministic. Nobody knows when it's going to fail. It's totally unpredictable. That's clearly non-deterministic. Question?
A fork join pool is an abstraction above port.
A fork join pool. Yes, you can. A fork join is where you have two threads. A thread creates another thread. Forks. You have two things, and then the join brings them together again.
Yes.
Yeah, you could implement that using ports. It's not so. I mean, you have two threads basically, and then they kind of synchronize together. Yeah. So the question is that there are other abstractions than ports. You can do fork join, but fork join can be deterministic. Fork join is not a non-deterministic thing. So somebody mentioned fork join as implementing on top of ports. You don't actually need ports to implement this. This is actually deterministic. This is actually declarative. Okay.
And if you have a pool of threads in between?
If you have a pool of threads, okay, if I have a pool of threads and I pick one to do the task, then it's non-deterministic because you're choosing a thread, okay? But the basic fork join where I create two tasks and then I combine them, that's not, that's still declarative, it's not non-deterministic. You have to be careful, So you have to develop a kind of feeling for non-determinism, okay? So now I'm telling you kind of intuitive things, So this is the last lecture of the course. I'm assuming that you kind of understand. We've been through this before, so I can be a little bit more philosophical now, to give you more deeper understanding, So non-determinism is an important thing, and people who don't do computer programming, they don't understand that. Even smart people like physicists who think they're extremely smart, hello, all the physicists on YouTube, they don't understand really the notion of non-determinism as it's visible, as what it means is that there is a choice that is done by someone who is external to the program or to the part that we're looking at. So this is a very important idea, and this is one of the things I want you to keep in this course. Non-determinism is very important. Of course, I can ask on it on the exam, but it's also a very important thing. So you have to develop kind of a nose for what is non-deterministic. For example, a consensus algorithm in a distributed system is clearly non-deterministic because we don't know who's going to win the consensus. Whereas something like a broadcast algorithm is deterministic because everyone is receiving the same thing. Okay, so you have to it's interesting when some things are deterministic, some things are not. Okay, so let me go on now. So we have these other paradigms. Let me say a few words now about other things. Let me say a few words about data abstractions. Okay, so data abstraction is orthogonal to the declarative, non-declarative divide. Data abstraction is a way of organizing your program as a set of separate pieces, partitions. So it's organizing the program as basically independent parts with their own specifications. So here's a data abstraction. You have an interface, you have an inside and an outside, and it does something. The interface obeys some kind of rules that you have to obey. If you don't obey the rules, then the abstraction can punish you, or the program crashes, or it just doesn't work, okay? Or it says this is illegal. So there you have to obey the rules of the interface, and this boundary is unbreakable. You cannot traverse it. Okay? If the language is well designed, you have an unbreakable boundary here. You cannot look inside. You can only go inside through the interface. And if it's well designed, the language will enforce it. Of course, sometimes languages let you cheat, okay? They don't really believe abstractions. For example, a language like C++, it completely cheats, okay? Where a language like Java is okay. JavaScript also completely cheats, okay? Whereas a language like Java, you can build packages, classes, which are completely opaque and invisible from the outside. You can only do the interface. So this is very important, huh? If I have a program, a big program with many abstractions, like an operating system, millions of lines of code, huh? And it's built by hundreds of people. This is the only way to make a system with large numbers of people, okay? Okay, so that's the abstraction idea, but the programming language has to support it, okay? So you need language support for this. Some languages have very bad support. I'm looking at C++, hello, C++. Some languages have better support, like Java and many modern languages. Now, C++ has bad support because it was never designed to be data abstraction. It was designed for writing extremely low-level code, like an assembly language, which has no abstraction boundaries. Huh? C++ was designed as a readable assembly language, so it doesn't really support abstraction. Whereas Java was designed as a big, for making large business applications, so it does support it, okay? We have three concepts in the language that support this. The main one is lexical scoping. This took a long time to get accepted, until the a long time. Now it's been a while. In the 1960s, this was not known. It started becoming known in the 1970s. So you need lexical scoping, also called static scoping. The second one is higher order programming. So higher order programming is that these two are already covered by lambda calculus, actually. Yeah? The lambda calculus already covers them, which is interesting. Huh? The lambda allows you already to build abstractions in the lambda calculus. But it's not enough. There's actually a third concept, which is more like a, a form of encryption. Basically the notion of a key and a locked box. The notion that you can actually close something inside and lock it. So the key is basically an unforgeable constant. And the locked box is actually a structure that you cannot look inside unless you have the key. Okay? So in Oz we have concept, the key is called a name, and the locked box is called a chunk. So this is a strange name, but it's actually a record that only has the dot operation. It does not have arity. That means if you don't know the name of the field, you cannot look inside. So you can lock the box. This concept is a separate concept, and that if you don't have it, you miss some things. Okay? So there's two kinds of data abstractions. They are objects and abstract data types. They are, again, fundamentally different. If you look at the mathematics of it, they are fundamentally different ways of organizing data. And we saw this one objects where you have only one kind of entity, and ADTs where you have two kinds of entities. So this is again a fundamental distinction. Just in the same way that lambda calculus is fundamental for declarative programming, the object abstract data type distinction is fundamental, and you will see it in all programming languages, okay? And that's one thing. And then there's, of course, the declarative, so no state, and the non-declarative with mutable state. You can, of course, define abstractions that are declarative or non-declarative, okay? So that makes 2 times 2. So there's actually 4 ways to do data abstractions in all. So you can do the data abstractions here, no problem, huh? But if you're here, you can do more kinds of data abstractions, okay? The ones that have an internal state inside them. They are maybe easier when you interact with the real world, huh? These ones. Okay. One data abstraction that's very interesting that I want to mention specifically here, a really interesting one, which is now becoming very important, I call the functional object. So this is an object, like object to only one kind, but written declaratively. Okay? An object that's declarative. Okay, let me see. Let's see the time. I want to make sure that I say what I want to say here. Okay, so let me explain this. So it's basically an object. So you have one thing. You have one kind of entity, but it's also purely declarative. And this was very interesting because you do not need the keys for this. This one you can do purely with lexical scoping and higher order. This is actually a very interesting one. So I encourage you to understand how it works. Let me make a simple example. A stack object. Push X. Stack object X bar S, and I'll do a very simple one, pop X case S of X bar T, sorry, Y bar T, then X equal Y, stack object T, and this is the pop in stack, so I have a push operation and pop. Okay, and then I have the new stack operation, create a stack, and it's stack object nil. Okay. This is a very interesting piece of code. It's very simple in number of lines, but it's actually very, very special and smart. When I call new stack, I will create a stack. So what is a stack? A stack is a stack object. Initially, nil is the initial stack. So that's an empty stack. So if I call stack object with nil, I will actually have a record with a push operation and a pop operation. So this is the result of an empty stack. But this push and pop are this push and pop, and they see S. And S has the value nil. That means the value of the stack is hidden inside, okay? So the stack is nil here, huh? Which is an empty stack, huh? It's hidden inside because of higher order. You see that? When I call stack object nil, I return stack with two functions, push and pop, okay? And push and pop are both inside the lexical scope of S. S, which is nil here, huh? Which is the value of the stack. Push, if I want to do push, then I will call stack object with x bar S. So this is x bar nil, okay? If I call push, I will return a new stack object. So if I call push now with A, this will return a new stack object, okay? Which is again a record like this, stack, push, pop. Now here's the push, and here's the pop. This function, this push function, is not the same as this one, because this one now knows the stack A bar nil. You see, when I call push, I return another stack object. Okay? When I call pop, I return another stack object. So it's completely functional. The stack objects are like functions. I call the push and I return a new stack object, or the pop, new stack object. And the value of the stack is hidden inside, using higher order. And it works because of lexical scoping. So the lexical scoping means that the S is only visible here, and higher order. I create these new functions. So this thing is exactly behaving like an object with two methods. But it's purely functional. Okay? So this is actually a very nice example, because understanding this, you get it, okay? If you understand how this works, then you really understand what this means, okay? This data abstraction being both an object and functional, okay? So this is important. This is an important example. And the interesting thing is it's extremely simple. It's a very simple piece of higher order, and you don't need anything special for this. Only lexical scoping and higher order functions, okay? So this can be done in all declarative languages. You can do object-oriented programming in Haskell in a pure way if you want, no problem, okay? So that's nice, I think, Objects has nothing to do with mutable state, Okay, now we're almost done, okay? I still have a few things to say. But let me say just one more thing now. Let me talk a little bit about multi-agent, and then we'll be done, okay? Shared state, I will leave that for the slides, okay?
It's a closure.
Let me just say one more thing, and then we'll be done for the year. Let me say something about multi-agent programming, which is agents, basically ports with threads inside sending messages. Let me just say something about Erlang, which is a language based on multi-agent. So Erlang has a processes, which is basically very similar to what we call the port object. Okay. So Erlang, you can divide Erlang into two kinds of concepts. The concepts that are related to single processes, and the concepts that are related to multiple processes working together. So single process, of course you have send and receive. You send them. And you have an operation called linking. This connects two processes together. It's primitive. When one of them fails, the other one is notified. And the multiple processes, this is really the contribution of Erlang. These are called behaviors. This lets you combine many processes together. You have generic server, generic finite state, generic machine, generic event handler, and then the one that's really characterizing Erlang is the supervisor behavior. All of these behaviors are generic, okay? Which means that they're like higher order abilities. You can add the functionality, and they all are connected. So the supervisor can manage all of these, okay? This is a very important contribution of Erlang. So Erlang invented this idea here, and this lets you make extremely reliable software. This is the main contribution of Erlang. If you want software to be extremely reliable in a concurrent real-world environment, then Erlang is the best system for you, okay? And the reason is because Erlang has this piece. It has this notion of behaviors and supervisor behavior, which allows you to manage the failures of all of the other behaviors, okay? And they're generic. So that means writing an application in Erlang is very easy. You just have to instantiate the behaviors, okay? So it's actually very, very straightforward and very easy. Okay. I think that's saying there's a few other things. I could talk about transactions and two-phase locking, deadlock, which is important, safety and liveness. But maybe I run out of time now, but I have actually presented the most important things and the lessons of this course, which I hope you think about, okay? Let me say a few things about the exam now. So the exam will be combining theory and practice. I can ask you to write code, and I can also ask you to give formal definitions. So the formal explanation of why a declarative program cannot interact with the real world using the lambda calculus, I can ask you that, to explain that to me, and I can ask you to explain how you extend that to add mutable state, something we saw in the course. I can also ask you to explain how a lazy, persistent data structure works, and how the laziness gives persistence, okay? I can ask that. I can also ask you to write maybe some lazy programs, maybe some functional objects, this kind of stuff. So it's really a combination of theory and practice. I can ask you to write code, not many pages. There will be small programs, but important ones, and the formal definitions. Okay. Okay. I think that's good enough. I think you have seen many things now. So this is going to be the end of the course. And so I wish you all good luck for the bloggers. And hope you like the course.